Now what we're going to do is we're going to take everything that we learned and, no, I'm just joking, we're going to completely ignore it and talk about something completely different. How many of you like Monty Python?
What is it?
And now for something completely different. No. I need to learn me some Russian jokes. Okay. So, gentle introduction to reactive extensions. How many of you know reactive extensions? Okay. So, you said you didn't. Get out. This is not, it's very gentle, so I'm just going to basically explain an overview of what the idea behind reactive extensions is and show you different things that you can do with it and basically hopefully get you interested enough to kind of play with it a little bit more. That's what this is. So why? A lot of the things that I always talk about, I always want to start with the why, which is very, very important question you have to ask yourself. And because there's a reactive manifesto. So I read this and it says we have to go reactive. And I said, well, that's good enough for me, right? So if we have to go reactive, I will start to go reactive. Now, if you read this manifesto, which is beautifully published with interests of whoever publishes it, it talks about scalability. Nowadays, if you are doing something that is not scalable, just stop. It doesn't matter if you don't have more than 100 users. If it's not scalable, forget it, right? Silicon Valley is not interested. But nonetheless, what does the Reactive Manifesto tell us? The manifesto points to 4 things. Applications should be responsive, which is fair enough, right? That nobody has any objections to an application being responsive. It should be resilient, which, you know, it should always work. It should be elastic because scale, because Silicon Valley, and it should be message driven because of decoupling. Now, some of those things are okay even if you don't want to scale. Right? Message-driven, decoupling, resilient, responsiveness, those are all okay. But I mean, jokes aside, I'm not talking about this because of the manifesto. I'm talking about this because of this. How many of you remember this? This was beautiful, right? It was used to play solitaire, either playing solitaire or trying to win by drawing the solitaire winning, right? Back in the old days. That's what I used to do, right? I never used to win at solitaire, so I just used to simulate it. My life is hard. Anyway, so that's what asynchronous programming is, and it's hard, and we all accept that. Applications, though, require it, because whether you're doing a desktop application, you need that, you know, a lot of things are background processing. Whether you're doing a mobile application, that is, today, in this day and age, if your website or your mobile application doesn't respond within 2 seconds, 2 seconds, you've thrown that damn phone on the floor and you're pissed off and you just want to get the new iPhone, right? Web, because, well, web. There's a study that says if your web page takes more than like 3 seconds to respond, you could potentially lose 6% of your customers. I don't have that issue. Like, I mean, how many of you have gone to a website that's been too slow and you've decided to go to the competitor? Yeah. So I don't do that because in Spain everything is slow, so I don't have much option. But apparently there's studies by those same people that want to sell you cloud that says that this is great, that you need it. And if you're doing server-side stuff, well, again, you know, we need to be responsive. So that's why we need it. Attempts to ease it. Threading. Who loves threading? Okay. Async await. Yeah. C# is beautiful. So C# has this thing called async await. And basically what you do is any method that you want to be asynchronous, you put an async in front and then you await it. And if you forget some await somewhere, forget it. You're kind of like, this doesn't improve anything. No, because 17 calls down the line, you forgot to put an await. It was beautiful. The promise was amazing. You prefix keywords async await, and then if you look at a code base now in C#, there's just async await everywhere. Futures in Java. You like those? No. Yes? Okay. Well then go. Leave. Anything here, if you like, just go. Really. There's some cold pizza left. Callbacks in JavaScript. Who likes those? You probably like JavaScript as well, don't you?
Not JS.
Oh, yeah. It's also known as the tilted Christmas tree. If you've ever seen the callbacks, is right, call this method, once it returns, do something. Of course, that method also needs to do something when it returns, so that one takes another one, and then you get basically like a tilted Christmas tree. And promises, which is JavaScript hipsters saying futures are great and porting them over to JavaScript. Now, all of these have issues, one way or another. First of all, combining asynchronous operations isn't that easy, right? If I have multiple async awaits coming in from different places, if I have multiple callbacks, it's not that easy to combine all of these together. And different techniques for different languages. So if I'm doing JavaScript, I have callbacks. If I'm doing Java, I have futures. If I'm doing another type of Java, I have composable futures. If I'm doing C#, I'm doing async await. And our brain capacity is limited, right? And every time we have to deal with different paradigms. So I personally say, let's keep our brain cells to learning IntelliJ shortcuts, not this, okay? We've run out of keyboard shortcuts in IntelliJ anyway, so that's done for as well. So there we go with reactive extensions. Reactive extensions is trying to solve this. It's trying to bring the same programming paradigm to the entire kind of ecosystem, independently of what language, what technology, whatever it is that you use. If you look at reactive, it says that it's an API for asynchronous programming with observable streams, right? So that is very important because everything is stream, which, and also what's more important, it's that it's observable, okay? Following? No, you probably didn't understand anything I said, which is great. Let's take a step back a second. What is programming?
Solving problems.
Solving problems. That's deep.
Creating problems.
Creating problems. I like to call it creating a self-sustainable industry, but that's a different thing. So programming is an art. You didn't see that coming, did you? No, and we are craftspeople. You probably didn't see that one coming either. And all we do is just process data, right? We try to become luxurious and glamorous and all that, but it's nonsense. All we're doing is just processing data. We're data crunchers, right? Just like whiskey. We take primitive elements and we process it. Except whiskey is beautiful, we produce crap. Back in the old days, we used to sit in these things and process data. Nowadays, they call it open floor plans. I just think they're saving costs, right? And saying that it's more social, no, it's just saving costs. Before it was more expensive to have cubicles. By the way, there's a study that says that this is just wrong. It's very unproductive. But there's so much money in Silicon Valley to throw at hiring developers that it doesn't matter. It's fantastic. Anyway, enough of that. That's data, we process it with a function. Lambdas. How many of you are familiar with lambdas? Right. I mentioned this a couple of times, but I saw a tweet a couple of months ago that said that functional programming is this radical new paradigm. It was a JavaScript person that said it. Anyway, so data comes in various forms. We have scalars, date of birth, sales amounts, names. Collections, we have list of countries, collections of customers. But ultimately what we're doing is just taking individual values or collection of values and converting them back and forth and making a very, very beautiful interface to a database. That is our life. Now let's take a step and stop and take a look at processing data functionally. This is like a crash course in functional programming. How many of you know what functional programming is? It's a radically new paradigm that just invented 80 years ago. So let me show you an example. Right. This is code. Good. Now, this is numbers 1 to 6. This is a loop for number in numbers. Print line prints out each number. Okay? This is exactly the same thing, except it's taking a lambda, a function. right? And what it's doing is saying print the number. Okay, so it's a function, but this is a higher order function because it's a function that's taking a function. So if you dive in there, it's just a for loop, except it's abstracted away. But it's good because now you can say, what can you say? I'm doing functional programming. It is, you are, really you are. As soon as you pass in a function, you're doing functional programming. And it doesn't even have to be Haskell. And this is exactly the same thing, except we have this convention in Kotlin whereby if the last parameter to a function is a function, you can then drop the brackets. And you can also put it on a different line, which makes it look nice, because then you can create these wonderful things called DSLs, right? So that everyone's following that, right? If I print that out, it creates a bunch of things. Now what I can do, for example, is do more spectacular things. So here I have a list of numbers, and what I do is I call filter on them, and what that does, it just, you know, filters out. It is a convention in Kotlin, which basically means if the lambda has a single parameter, I just call it, kind of like Groovy. So here, if it's even, then if it's even, I filter out the even numbers, and then I return a scalar, which is the last one, and then I print that. And then you can do things like flattening, like using things like, filter and map to map one value to another value. So map basically takes a collection of items and maps it to another collection of items. And all these things. Everyone understands that? Yes? All clear? How many of you are doing this nowadays? With Java 8 probably. Right. If you can't use Java 8, your salvation is here. It's called Kotlin. And this segment was sponsored by JetBrains. Right. Okay, so everyone's clear on that. So there you go, a crash course on functional programming. Now we all do functional programming. In the old days, it was called LINQ in C#. Right. Actually, that's what it was called, LINQ. LINQ in C# is functional programming, except it was a way to introduce functional programming in C# without scaring everyone off. So they said, look, you can query your database from C#. What we're doing here is, don't laugh, it's true. What we're doing here is an iterable, which is an enumerable or an IEnumerable in C# again. So here I have an iterable that's an iterator. And what I'm doing is basically iterating over data, right? I'm calling next, has next. When I do a for each, all I'm doing is just iterating over this data. Just iterating over and over again, getting the next value. The problem is that when I'm doing these iterations, what is causing that is a blocking call. So when I do for each, what it's doing is blocking the call. And until that call doesn't end, I can't continue further. Right? Which is okay because this is instant. But if you take this and, for example, add something that's more time consuming, now I start to block. So now if I do this, for example, in an application where I have a main UI thread and I do this on that UI thread, this is going to cause a freeze. Because all of this is blocking. It's looping over data, it's making calls, it's getting those data, and it's just blocking on those calls. But we shouldn't block. That's what asynchronous programming tells us. But we're blocking because we're waiting for data. So why not just get notified when data is available, as opposed to block? Why not just someone say to me, hey, data's available, do something with it? We're all accustomed to this. If you've ever done any kind of WinForm programming or any kind of programming, it's called on-click, right? On data changed, on Dropbox change, on whatever. It's just events. On data ready event. Let's assume I have an on data ready event that fires when there's data available. So instead of me blocking, let me just say when some data is available, let me know. That's also called the observer pattern. You're all familiar with, right? I'm observing something, and when something happens, I get notified. So going back to this iterable and iterator, instead of pulling data, why don't I do something else, which is notify? So instead of pulling, what I can do is push data. And I create a dual of the objects I have. So I go from iterable to observable, and from iterator to observer. Right? So you see, I'm creating a dual. And instead of calling next, I say on next. And instead of saying on has next, I say on completed. And then I add a new one here, which is called on error, which is fantastic, which also tells me if there's an error. So what I'm going is from a pull model to a push model. That's going to push me data, that's going to notify me when something's available. And this is a concept called duality, right? And I'll read this because it's really, really interesting, and it also shows my brilliant linguistic abilities to read English. In mathematics, a duality, generally speaking, translates concepts, theories, and mathematical structures into other concepts, theories, or structures in a one-to-one fashion, often, but not always, by means of involution operation. If the dual of A is B, then the dual of B is... There you go. Involution function is a very fancy way of saying f of x equals x. Here's an example of duality, right? And what we've actually done there is apply duality. How many of you know Eric Meyer? Eric Meyer is one of the guys behind C#. He's also the guy behind Link, and he's also the guy behind Reactive Extensions, right? And his company is called Applied Duality. Then bing, light bulb moment, right? Okay, fine. What's the difference between an array and events, he said? What is the difference between an array of elements and an event? Nothing. I have data that I'm pulling, I have data that I'm pushing. There's no difference. If I treat everything as an event, there's no difference. I have an array of numbers, I have a mouse that's moving. Every time the mouse moves, it shoots a coordinate to me. There's no difference. Treat everything as events. And reactive extensions is nothing more than just an extension of the observer pattern with some operators that allow you to work with data, combine their data, compose this data, and what it most importantly does is abstract away all that low-level threading that we all hate. Okay? That's it. Any questions? No. Brilliant. Let's continue. Any questions? Really? No? Okay. So one of the other advantages around reactive extensions is that now it's available for everything out there. So if you're doing Java, you have RX Java. So what happened is Eric Meyer created reactive extensions like 10 years ago on C#. But back then it was the evil Microsoft, and nobody took care of nobody loved Microsoft. Now it's the new open source Microsoft that everybody loves, or Microsoft says they love everyone. And it was funny, I was at a conference and Microsoft had a Oracle. It was the 20th anniversary of Oracle, right? It was a DevOps. And Oracle, sorry, I'm sidetracking, but it's interesting, I promise. And Oracle booth had this cake, right? And on it, you know, it was like the 20th anniversary. Microsoft booth had a cake, and on it it wrote, Microsoft loves Linux. They cut the cake. Oracle's cake went in like literally 2 minutes. Microsoft cake was there 2 days later. So, RX Java, what happened is that Ben Christensen, a guy that at the time used to work for Netflix, started to say, I really like this C# reactive extension stuff. It's now gone open source. What I'm going to do is I'm going to port this to Java. And thus was born RX Java. Okay, and then Eric Meyer contributed to RX Java. And then from there, it just, you know, took off. Now there is RxJS, because there are JavaScript programmers in the world. C#, RX.NET, Scala, RX Clojure, RX CPP, RX Ruby. Is Ruby still a language? Is it still a thing? No. RX Pi, RX Groovy, RX JRuby, RX Kotlin, which establishes Kotlin as a mainstream language, by the way. I'll stop with the advertising. Anyway, actually, to be honest with you, I'm using RX Java. All the demos I'll show you, I'm using directly RX Java. I'm not using RX Kotlin. All this is just a thin wrapper around RX Java to provide you with an even more idiomatic Kotlin. But then what also there is frameworks that leverage these APIs. So I have RX Netty, which is an adapter around Netty to work with observable streams. You have RX React, which is to work with React.js, which has nothing to do, by the way, with reactive extensions. But Facebook said, let's create a new framework and let's call it React. Why? To confuse people. So now we have a conference in Bulgaria that's called Reactive Conference that has nothing to do with RX Java. It's React.js. RX Android and RX UI. RX UI is for Cocoa, iPod, iPad, all those pods, eyes, development. Now it's all just demos. Lots and lots of demos. Okay, so what I want to start with is show you something that you should never do, which is a great way to start. So, two things here. There's two things that we have to implement, right? I said the observable, the Rx is basically an observable and an observer. So here is an observable. And what I'm doing is, instead of writing all of this crap manually, I'm implementing a base class which is called observable of string. So this is what I do. I create a new project and I import Rx Java as a Gradle module, or if you prefer, as a Maven module. And then I implement observable of string, and then that has an overload constructed version, which is create a subscribable from an iterable. Don't worry for now. And then I pass in an iterable. And here is the observer. I say on next, print line, print the actual elements. On completed, print the actual sequence completed, and if there's an error, on error. So now I use this. I say create an observable, which is an observable, and I pass in an iterable, right? So I pass in a list of numbers. And then I create an observer, and then I have the observable, I have the observer subscribe to the observable. Clear as mud, right? So if you run this, really, really good, you get element A, element B, element C, sequence completed. Right? This is really cool. Yes? No, it's not. What have I just done? Introduced 17 classes for the sake of it. But we'll see why. Now, here is a refactored version. Here what I'm doing is, instead of creating an observable that implements an observable of string, I'm just passing in an anonymous object with a single method to call for any subscriber. So here I say on next A, on next B, on next C, and then my observer is pretty much the same thing, and I say observable subscribe, and if I run this, basically the same thing's going to happen. Element A, element B, element C, sequence completed. It's doing the same things. I'm just showing you different ways to do it, and now you'll see that you never do this, really rarely. Here's a third way, a little bit more cleaner. I create an observable of create. Instead of passing an anonymous object, I'm passing in a lambda. And here I say create a subscriber and loop through that and list A, B, and C, and then call on completed. The observable, I'm just subscribing with a lambda expression as well. I'm not creating an object. I'm just subscribing to it with a print line. So I've saved a couple of objects, which is always well appreciated. Okay? That is how you create an observable, an observer. And what's basically happening is that the observable is emitting elements, and any observer that's subscribed to that is receiving those elements and doing something with those elements. It's that simple. But if you think about it, it's nothing different to what I did here. Really, I'm doing the same thing, except there's a lot of magic going on under the covers. And that magic is that this is no longer blocking. Right? So this code no longer would block. This would continue down, and you could do other things, and then once it's done, it would handle act. Okay? We'll see this see how it works. Now, I said that all of these things that I've showed you is something that you wouldn't do. Why? Because RxJava comes with a lot of operators and a lot of overloads and a lot of constructors that allow you to do common operations much faster. So instead of doing all this, or for example, all this, what I can simply do is say an observable from, right? And what I pass in is there's a method from, right? Which is you can see that it's a static method, factory method, that I pass in a list of elements. So I pass in an iterable, and it takes more than an iterable. It can also take a future. It can also take an array. So it takes whatever you give it, and it converts it into an observable. Now I create an observable from a list. And here I'm subscribing to that. What I'm passing in here is 3 different lambdas. 1 for on next, 1 for on error, and 1 for on completed. Okay? And then I'm saying observable subscribe. And this is just another subscriber. So let's remove this, and let's remove this, and let's run this and see what happens. I get element A, element B, element C sequence completed. So I got exactly the same as the first example, except now it's just so much cleaner. I just give an iterable or a future, and I get back an observable. I'll tell you what that is in a minute. Later on, we'll come back to that. So what I can also do is, now this is great, I've created an observable, but one of the things that you can also do with these observables is act on them. So here I'm creating an observable, and then what I'm doing is I'm filtering those out, I'm then mapping them, I'm then filtering them again, and then I'm printing them. So running this, I get some numbers. Okay? Now a couple of things here. Notice that first of all, I have no subscribe. Do you notice? Because for each implicitly subscribes. Okay? Second of all, what am I doing here? I'm just doing functional programming. Well, yes, because I'm passing in lambdas. But I'm just chaining, I'm doing pipelining, right? I'm taking an observable, I'm acting on the result. The result of that, I'm combining, passing into another function. Then I'm passing that into another function, then I'm passing that into another function, and then doing something with the result. Which is exactly the same as I showed you here. It's the same thing, right? Filter last, except here I have a few more calls, right? What will happen is that in about 7 years now, we will have like 16 chained calls, and then and then someone will say, but I thought functional programming was about creating cleaner code. No, because we're developers. So, but the difference here is that this is not just getting back a collection, and that's the key thing. This is actually getting back an observable. So filter returns an observable. And then on that observable, I can call another observable, another function that returns another observable. Right? So if you look into filter, this is a different filter from the filter that you saw. You see, this returns an observable of t. It doesn't return a collection of t. And this is allowing me now to combine results. But the key thing here is that this is asynchronous. Let me show you how. An interval. Here's another factory method. What that does is very similar to from, except it does nothing like what from does. But it's very similar because it's a factory method. What this does is take a number and a unit, right? So it takes an interval and a unit. And then it's just going to spit out numbers. So if I run this, it says it's just going to sit there and say observe 1, observe 2, observe 3, observe 4, and just go on, right? What do you think will happen if I remove this? Oh, come on, this is way too easy. What's going to happen?
Same result.
Same result. No. Because that's non-blocking. Right? That's the key thing. We've gone from blocking calls of pipelining of functions to non-blocking. It didn't have time to do anything. It went on its own thread, and we'll see which thread it went on, but it went on its own thread. We can try and get a result by maybe doing something like nanoseconds. Let's see if we do nanoseconds, something comes out. No, but I bet if I run it again, something might come out. No, but if I run it again, something might come out. There you go. See? So at some point it comes out, but this was because it's on a different thread. And this is the key to understanding this, right? It looks exactly the same as doing normal functional programming, but it's abstracting all of the threading away from us. Right? It's putting all of that asynchronous programming under the covers and surfacing things that we are very familiar with. Okay? So let's go to more. So for instance, what I can do here is combine observables. So here I have from 1 to 10, and then I have, for instance, A to J. And here what I do is I say take my numbers and zip them with letters. And for each one, I pass in a lambda to say how I want this to be zipped. Zip, basically what it's doing is just taking one from one and zipping them, right? Just creating a zip. This is exactly the same thing. The difference is that this is a factory method, this is a static method, whereas this is an instance method, right? So what this is basically doing is combining. So now I can have one observable here, one observable there, and then get the results, combine the results, and do something. Okay? So now one question that might arise here is that if each of these, for instance, is, I mean, this is instant, but imagine from is something that's long, you know, that takes long. How does that happen? Maybe the results that are coming in from this one might be faster than this one. And that gives way to something called back pressure, which we'll see in a minute how we can deal with. Okay? So let's see what else. Now, this is another example, which is basically the interval that we saw before. But if we run this and notice that it's seconds, it does work, right? It does work, and there's no while loop there. Why does it work? Because I have this thing over here, which is called to blocking. So what to blocking does is take an observable and block, and basically hold. Now that kind of feels like an anti-pattern, right? Why would I ever want to do that? And there are rare cases where you might want to, right? For whatever reason, maybe you have some, same as with semaphores, right? At some point you needed to have certain results and time it, whatever. You can actually do an explicit blocking and block the results of certain observables. Now, one of the things that we haven't seen is, but it has, is error handling. And that's an issue, right? Let's say, for example, you know, the observable gives me an error, or I want to try something and it fails and I want to retry. Typical example here. Let's say here I have an observable, and basically I've implemented a random rubbish code that you would never ever ship. And what this does is loop through a list of stuff, sleep for 100 milliseconds, and then if the number is divisible by 5, then throw an exception. Okay? Now let's comment and uncomment some code. So let's take this one and uncomment that, and let's take this one. And let's comment that. I'm showing you my IntelliJ skills here. So watch this. What I'm doing is I'm just mapping, received it, subscribe, print line. Everything you've seen until now. Okay? If I run this, what's going to happen is it gives an exception, right? 5 is divisible by 5, therefore it throws a random exception and it just quits. Now, look what we can do. Let's go ahead and block this. Here what I'm doing is I'm saying map the results and say I received 1, but retry once. So what's that going to do is if it fails, it's going to retry again. Right? So you're going to say, what? Imagine. Let's say that I say to you, I want you to go and check for a website, and I want you to retry 5 times in case there's a timeout. Imagine that. Instead of having a map of a loop of numbers, you can say retry 5 and do a get on a website. And if it fails, after 5 times, it gives up. How much work would it be for you to implement that manually? Quite a lot. And yet this is just a simple call, right? I could do retries with errors. See if here I say, sorry, retry based on conditions. I can say retry if it fails, only if this specific scenario, in this case, like if it's a number exception, then fail or ignore it, and based on specific conditions, right? So really easy to implement certain types of recuperating from errors. Now let's put something together. So let me run this server. I have a file server, I think, or a socket servers. So this is just basically I've thrown together some sockets that are going to start to print out some stuff. There's a file server that's going to send some log data from some website. There's another file server that's going to send something else. And what we're going to do is I'm going to run this, right? And so I'm going to run these sockets, and now these sockets are running. And then I'm going to come back here, and I'm going to do some reading from sockets. And what this does is basically it's going to read from the sockets, and it's going to filter out a specific string. For instance, here it's going to filter out any log entry that contains twiki bin rdiff main, and once it finds that, it's going to print it out. So I can now run this, and this starts to run. And it's continuously reading from that socket, and as it reads from that socket, if it finds this entry, it just prints it out. Right? Now you imagine, you can combine this with other observables and say, read from this weblog, map that if you find filter specific IPs that could be also found in a different weblog, right? And when you find those, match those conditions, then do something with that. And you just do that by simply just combining observables and pipelining the results, much like you would do in a functional way, except you're not blocking. And all of that is going on under the covers. And how does that work? Let's take a look at scheduling. So, as developers, we like to break things. That's a given. So take a look at this one. Val observable from 1 to 10, observe, subscribe. What we've seen so far. What I'm doing here is I'm printing out the thread name. Okay? Thread name is simply a function that just gets the current thread. And I'm going to run this. You see that the main function here is just going to run that main one. So let's go ahead and run this. And you see receiving 1 on main, receiving 2 on main, receiving 3 on main. It's executing it on the main thread, which is why it works. Now, remember the interval one that needed the while loop. Let's see what happens if we try and run that one. By the way, this is ideal for UI programming, right? Because you just make it so much easier than having events firing off in all different places. So watch what happens now. The thread main executes, which is printing this line here, but the interval is automatically selecting some other thread. That's why it would never run when we ran it before, because it's not executing it on the main thread. It's using this other thread, which in RX is called RX computation thread pool, right? So it's executing that on a different thread. Now what we can do is we can actually tell RX what thread I want to observe on, what thread I want to subscribe on, which is where we can really screw things up. So here what I do is I say from 1 to 10, but observe on schedulers computation. And if you take a look at this, there are schedulers. It's basically threads abstracted under the concept of schedulers. So I have computation thread, I have IO thread, etc. So if I run this one, you can see that I'm running on RX computational pool. So this is the same from as before that was before running on the main thread. Now I can switch it to run on the computation pool. And much the same way, I can say subscribe on a different thread, right? So I can define where I want to subscribe, where I want to observe. Okay? Now normally, you don't necessarily have to do this chaining. In fact, if you take a look at the majority of factory methods, they always recommend that even when you're creating your own observables, add a new parameter, which is the scheduler. So instead of doing subscribe on, what I could do is pass in the scheduler here, right? If IntelliJ worked, what I could do, no. So what you could basically do is pass in the scheduler there, okay? Now, okay. So, one of the things important to take into account though here is unsubscription, right? This is not magic. What it is doing is basically getting information and then pumping it to you and in a synchronous way. At some point, you could run into an issue because if I'm using memory to accumulate all this information, I need to, I can run into a memory problem, right? I could get out of memory exceptions. So every time I create an observable and that observable returns an observable, what it's doing is actually taking the collection that's coming out from the first observable and then is applying this operation to it, which is called lift. And what lift does is create a new observable from that collection. But at some point, all of this, as soon as, if I have a chain of observables, when the first one emits, it's going to pump it down to the second one, right? And the second one to the third one. If I unsubscribe, I need to notify the chain that I want to unsubscribe. And that's why when you're implementing observables, you need to take into account whether you have anything subscribed. If you don't have anything subscribed, stop doing what it is that you're doing. And that could basically save on memory. But the other issue is with terms of buffering. So imagine I have something that's reading from a weblog and then something that's coming from a user interface, and the speed of this is much slower than the speed of that, right? And I want to combine the results. How would I do that? There is no magic way. I mean, the one observable can produce an overflow, can create an out-of-memory exception because it's waiting for the other one to come, which goes at a much slower pace. There are a few operators inside Rx that allow you to kind of handle these things. One of them is called buffer, which basically just says buffer every 3 elements and then emit it to me, right? The other one, for instance, is called debounce. And a very typical example of this is, let's say that you're creating, because you can do this with RxJS, let's say you're creating a web page where you go to Google and as you type, Google suggests, right? Now, every time I press a key press, naively in the old days, what did we do? We would send the request back to the server. That's crazy, right? So what you can do is say, for example, debounce, and that basically means wait 3 seconds. Once 3 seconds have passed, then notify, right? But there is no magic solution to having one observable and another slower observable and somehow magically do that. The other option is to just basically discard elements. Now, everything that I've shown you now, up to now, is called cold observables. And what does that mean? If we go back to the initial one here, and let me uncomment this line, watch what happens. Nothing, right? Let's now uncomment this. So you see that the second observable has again started from the very beginning. These are called cold observables, and by and large, every observable is cold. That means that every new subscriber basically gets the same sequence of data over and over again. Every new subscriber kind of initiates a new observer, or a new observable, right? However, there are also hot observables in the world. For example, a mouse is a hot observable. What is a hot observable? As I move the mouse is emitting data, coordinates. If I subscribe to those, everything that was emitted in the past, I've lost, right? That's the difference between a hot observable and a cold observable, okay? So it's very kind of hard to simulate a hot observable, but here I've tried to kind of do it. So you see what happens here. If I run this, you can see that, for example, here I'm taking 5 elements. So you see that I'm subscribing to this observable, but you see that the second one doesn't start from the beginning. It just continues where the observable was left off. Okay? By the way, one thing that I didn't mention about the scheduling, one good thing about this is when it comes to testing. Since constructors can pass in the actual scheduler, look how you can do some testing. Because ultimately what you're doing here is you're testing time, right? You're essentially testing things that are happening in time. So here I have a test scheduler which comes in the box with RxJava. And what I do is I have an array of numbers and I say emit every interval of 1 second, take 5 elements, subscribe, and add the numbers. And then I have some assertions. And then in the test scheduler, I say advance time by 2. So it's simulating time, right? And I could actually simulate what would happen when I run this. So if I run this test, it would say that, it's passed. And if I, for example, say run, advance time by 3, then it should potentially say that it's failed. And if I say 1, it should potentially say that it's failed. Yes. Okay? So that allows you to do some kind of testing. Okay. So, any questions? Is this the silver bullet? No. There is no silver bullet. You know that, right? If not, come to Moscow and I'll tell you there is actually on Friday. Where RX helps? Everywhere actually. Kind of like really everywhere. Asynchronous code, it kind of helps. Yes, because that's what it's built for. For combining results, for events, for errors. So you can use it for UI programming. You can use it for JavaScript programming with RxJS. In fact, it's much more beneficial than all of the other crap that we have to handle nowadays. But most importantly, it just adds a layer of abstractions, because that's what it's basically doing. It's abstracting all the threading, all of that horrible stuff away from us and giving us a layer of programming API that is similar to what we're already accustomed to with kind of functional programming and pipelining results. The issues that it has is it has a learning curve, right? It's not simple to grasp. You have to think in functions. You have to always think in streams and how to combine these streams. You can still cause havoc with your code, because if you start to, for example, subscribe on a specific scheduler and observe on a different one that doesn't make sense, that could produce deadlock. It doesn't automatically give you parallelism, right? What it's doing is providing you with asynchronous callback handling. To learn more, I recommend going to this site, which is called reactivex.io. There's a whole bunch of tutorials and everything there. And there's another really good site, which is called RX Marbles, which is really good because it provides you with all of the ways in which you can see all the different operators that RX has and see it live. So RX Marbles. If you go here, it's interactive diagrams of. So for example, I have these. See, it's so beautiful. It's like anime. It's like the old days when you used to get the animated like GIFs. So you can move things here, and it shows you what all of these different operators do. So with last from, it tells you what would happen as you move these marbles along, which is a good way to understand some of the different operators, methods that are available for RX. Okay? And let's go back to the slides. And thank you.